Hello students, so we are starting with numericals based on pumps, then hydraulic turbines and windmill or a wind turbine. So this is the last topic in this unit number 1, that is introduction of energy sources and its convergence. So we'll see the problems based on hydraulic pump, then hydraulic turbine and windmill. So first example, we will see the first problem. Determine the power required by a pump to raise 2 meter cube per minute of water. So we have to raise 2 meter cube per minute of water to a reservoir at a height of 10 meter. So this is the head or height is given. If efficiency is 100%. So this problem will be asked in exam up to 4 to 6 marks. So we'll see how to solve this problem. So first, if you see, what are the given data? The first one is Q, that is the pump to raise the 2 meter cube per minute of water. So Q is equals to 2 meter cube per minute. Now, in any problem of turbine or pump, you have to convert this Q should be in meter cube per second. So we have to convert this unit meter cube per minute to meter cube per second. So we have to divide by 60 to convert minute into second. So 2 divided by 60 into meter cube per second. So it is your the capacity of the pump. Second, head, that is height is given 10 meter, and the efficiency of pump is given, that is eta is equals to 80%, which is nothing but the 0.8. So this is the 0.8 as a efficiency. Now we will have the next, we have to find out the power required by the pump. That is nothing but we have to find out input power to raise this water at a height of 10 meter. So first, we will calculate output power required by pump to raise the water to the reservoir. Now, the main function of pump is to convert electrical energy to the mechanical energy. So output power, it is nothing but the mechanical energy. That is nothing but your discharge. That is nothing but the pressure energy, discharge, and this height. So power, output power, that is PO is equals to rho, that is the density of water, G, gravitational acceleration, rho G, Q, it is the capacity, and H is the head. And this is 10 raised to 3. It is converting for power watt to kilowatt. Okay, so it is rho GQH into 10 raised to minus 3 kilowatt. So we have to put the value, that is 1000 is the density of water. If it is not given in problem, we know the density of water is 1000. Then G is, we know again value of G, 9.81 meter per second square. That is nothing but the gravitational acceleration. Now we have Q, that is 2 by 60. It should be in meter cube per second. Then H height, 10 meter, it should be in meter. So if you see this rho, it should be in kg per meter cube. That is, it is 1000 kg per meter cube. G, it should be 9.81 meter per second square. Q, it should be meter cube per second. Therefore, it is 2 by 60. And it should be in meter. So after putting this value, we get the output power required by pump. It is 3.27. Now, next we have to find out the input power. So power required by pump, that is input power, it is given by efficiency is equals to output power upon input power. So it is efficiency is equals to PO upon PI. So efficiency is 0.8. Output power is there 3.27 divided by PI. So we get PI is equals to 3.27 divided by 0.8. That is 4.09 kilowatt. So power required by pump is 4.09 kilowatt. That is nothing but your input power. Okay. So this is the first problem. In this problem, main important things, it should be conversion of unit. So we have to convert that Q to any value. It should be converted into meter cube per second. Okay, it is if it is liter, if it is meter cube, or it is in minutes, or it is in hours, we have to convert into in meter cube per second. Okay, this is the main concept. Now for pump output power, it is nothing but the this formula, that is rho g q h. That is nothing but the output. Output power is nothing but the mechanical power or hydraulic power or hydraulic energy, and input power, it is your electrical energy. Okay, so input power is electrical energy. So electrical energy, that is nothing but the power required to drive the pump. It is 4.09 kilowatt. So this is the first problem. Now we will see the second problem. So second problem is a water turbine. This is the turbine problem. So water turbine, this is the second problem. 2. A water turbine, it receives water from a reservoir under the head. Now this is the head. Head means height. So it is head of 50 meter at a rate of 900 liters per second. Now we have to convert this 900 into meter cube per second. The turbine discharges water at a rate of 10 meter per second. So the discharge from turbine is given. So we have to find out input power, output power, and the efficiency of turbine. Again, density is given, that is rho is equals to 1000 kg per meter. Now in water turbine or hydraulic turbine, we convert hydraulic power into electric power. Hydraulic into electrical power. So in this case, your rho qgh formula, it is at input point, EI. In pump, it is output. Here it is input. And electric power, it is your output power. Or electrical energy, it is your output power. So given data, so we have available head of 50 meter. Now discharge from pipe is given, that is Q, 900 liters per second. So we have to convert into in meter cube per second. So it is 900 divided by 1000. So liters into meter cube, we have to divide by 1000. So 1000 liter is equals to 1 meter cube. So 900 divided by 1000, that is nothing but the 0.9 meter cube second. Now again, velocity is given, velocity of water at discharge point from turbine. So C is the velocity. C is equals to 10 meter per second. Now we have to find out input power, output power, efficiency. Now here input power is rho qgh, same formula, rho gqh into 10 raised to minus 3. In turbine it is input power, in pump it is output power. Only this difference is there. Now put the value. Rho is 1000 kg per meter cube, g is 9.81, that is meter per second square, into 0.9 into 50 into 10 raised to minus 3. It is nothing but it is in kilowatt. So into 10 raised to minus 3 we have taken. So direct it comes into kilowatt, that is 441.45 kilowatt. If we cannot take this 10 raised to minus 3, then it will comes to be in watt, that is 441.450 Newton meter per second, that is nothing but the watt. So we have find out this input power, that is 441.45 kilowatt. Now we have output power. So we know that output power, it is nothing but the energy leaving from turbine. It is nothing but the kinetic energy of the water. So it is mass into velocity square. One half mass into velocity, that is 1/2 mv square. V के जगह हमने ये c कंसिडर किया है. So velocity is in c, so it is kinetic energy 1/2 m into c square. So 1/2 900 into c is 10 meter per second square, it is in watt. So it is 1/2 into 100 into 1000 100 tens of square, it is 100 into, now we have to convert this watt into kilowatt, so we have divided into 10 raised to 3 divided into 1000, or we can say it is 10 raised to minus 3. So kinetic energy leaving, it is comes out to be 45 kilowatt. Now output power is nothing but the input power minus kinetic energy, that is the energy loss. So input power is 441, energy loss is 45, so your output power is 396.45 kilowatt. Now we will see the efficiency. So efficiency is nothing but the output power upon input power. So output power is 396.45. Input is 441.45 kilowatt. So it becomes 0.8981. That is 89.81%. It is the efficiency of the water turbine or turbine. Okay. So this is the problem based on turbine. Now next problem, which is of a wind turbine. Now it is of windmill, or it is also called as a wind turbine. So an offshore wind turbine has a radius of 80 meter at wind speed of 15 meter per second. If density of air, it is 1.2 kg per meter cube, and efficiency factor, that is efficiency is 40%, find the power generated by the windmill. So we have to find out what will be the output power of this windmill. So given data, that is radius is given, turbine, it is of 80 meter. Then wind speed is given, that is velocity or speed, 15 meter per second. Then it is air density, it is 1.2 kg per meter cube. And the efficiency is given 40%, that is the 0.4. Now we have to find out the power generated by windmill. So its formula is main formula, the power generated by windmill, P is equals to this is pi by 2 r square, or we can say pi by 4 into d square. It can be taken as anything. So it is pi by 2 into r square into rho into velocity cube v cube into efficiency. This is the formula for power generated by the windmill. That is pi by 2 into r square into rho into v cube into efficiency. Or another formula is there, that is P is equals to, यही फॉर्मूला हम ऐसे भी डिराइव कर सकते हैं. इट इज 1/2 रो ए v cube into efficiency. Now here A is nothing but the area. So area is, either we have taken in either it may be pi r square. If radius is there, it is pi r square, or it is pi by 4 d square if it is diameter. So it is pi by 4 d square. Both are same. So therefore it is taken as pi r square. It is nothing but the, and this 1/2. So it is 1/2 into pi r square rho v cube into efficiency. So pi by 2 into 80 square, radius is 80, density is 1.20, then velocity, wind speed is 15 meter per second cube, and this is 0.4. So that is comes in watt. So therefore it is 16.286 into 10 raised to 6 watt. Now we know that 1 megawatt, it is nothing but the 10 raised to 6 watt. So we convert this unit into a megawatt. That is P is equals to 16.286 megawatt. Okay, so watt to megawatt. So 1 megawatt is nothing but the 10 raised to 6 watt. So this is the simple example that is power generated by wind. Now we have next example that is again based on windmill. So a windmill of efficiency 41.28% produces 1200 kilowatt of power when it receives the wind speed at 12 meter per second. We have to find out the blade diameter. So blade diameter is D. Consider air density, it is given 1.19 kg per meter cube. Now given data, power is given, windmill, that is the output power or power. Then velocity is given, then density and efficiency. Now we have to find out the blade diameter D. So again, power generated by same formula, P is equals to pi by 2 R square into rho into V cube into efficiency. Now power is given, that is 1200. Now it is given in kilowatt, so we have to convert it into watt. So for converting watt, we have to convert this into 10 raised to 3. Then again pi by 2 into R square, we have to find out the value of diameter. So first we will find out radius, then we will find out the diameter. Into 1.19 into 12 cube into 0.4128. So after calculation we get, and after square root we get the value of R is equals to 30 meter. So diameter is nothing but the 2 into radius. So it is 30 into 2, that is 60 meter. So this is again a small example where a blade diameter, or we have to find out the radius. Now in last, radius is given, we have to find out the power. Now here power is given, we have to find out the radius or diameter. Now next problem is again based on same wind turbine. Here again we have to find out the diameters, same. It generate a power of 6 kilowatt at wind speed of again 9 meter per second. Then speed is 120 rpm. Now here speed, angular speed is given. Assume overall efficiency of turbine as 40%. Air density is there, and wind speed is also given. Wind speed is also given. So we'll see this different types of application. We can say how to find out this diameter of wind turbine. So first output is given 6 kilowatt, then speed 120 rpm, efficiency 0.4, and wind speed 9 meter per second. So we have to find out diameter. Same formula we can take. Efficiency is equals to Pu upon Pi. So from that we can directly find out the input power. Now this input power is equals to kinetic energy. So that is nothing but the 1/2 mc square. Okay, so it is 1/2 m is nothing but the rho AC. That is nothing but the density into volume. It is nothing but the mass. So it becomes rho AC cube. Now here area again pi by 4 d square. So I have taken this pi by 4 d square. You can take pi r square or pi by 4 d square, anything. So after calculation we get this after putting some value, that is input power is 15 kilowatt. So converting into watt, 15 into 10 raised to 3 is equals to 1 by 2 into 1.20 into pi by 4 into d square into 9 cube. So we get the diameter of wind turbine as 6.608 meter. So we have next problem, which is based on again a pump. The capacity of overhead pump is 2400 meter cube, that is 2400 meter cube. Now it is the capacity given in only meter cube. This required to be filled by a pump which required to pump water up to height of 18 meters. So head is given in 40 minutes. So time is also given. Find out power requirement. Now here we have to find out for first Q. So Q is nothing but this meter cube per second. So we have to divide this 2400 divided by 40 minutes. So minute again it converted into a second. So we get H. Now here volume is given and here time is given. So we know that Q is equals to volume upon time, V by T. So V is in meter cube, time should be in second. So we can find out this Q. So power required by a pump. So wind power, it is Q is equals to V by T. It is 2400 divided by 40 into 60. So we get the value of Q, that is 1 meter cube per second. Now we have formula power. So power is equals to rho QGH into 10 raised to minus 3 kilowatt. So put the value 1000 into 9.81 into 1 into 18 into 10 raised to minus 3. We have to convert it into kilowatt. So we get output power as 176.58 kilowatt. So power required by a pump to raise the water to a 18-meter height of a capacity 2400 meter cube in 40 minutes. It is 176.58 kilowatt. So this is all about your we can say problems based on the turbine, pumps, and again the windmill. So we have seen the different types of problem. We have seen 2 problems on pump, 1 problem on turbine, and 3 problems on wind. So this is all about this unit. Now, if you are interested for unit number 2 also, that is introduction to thermal engineering, please subscribe my channel so that you get updated videos on that, and also like the videos and comment on that videos also. So this is all about these numericals based on pump, turbine, and wind. So thank you for listening this video. Thank you very much.